Okay, this is just kind of a supplementary video because there are a couple of problems on the Chapter 13 sapling homework that are really challenging, but I really like them, so I don't just eliminate them from the homework. I really like how they present a big picture problem solving sort of an issue. So anyway, this is, I believe it's question number 35. You can see it down there at the bottom. I have a 1.317 gram sample. It contains only vitamin C and sucralose, though we don't know in what ratio. It could be all vitamin C, it could be all sucralose, who knows. When the sample is dissolved in water to a total volume of 37.0 milliliters, the osmotic pressure of the solution is 3.97 atmospheres at 297 Kelvin. What is the mass percent of vitamin C and of sucralose in the sample? Okay, so this is, I think, just a really really interesting question that's going to stretch your brain a little bit to answer. So your numbers are probably a little bit different from mine. The numbers are randomly generated. And so I'll just show you how to answer my question, and you can reproduce the work with your own numbers. Where do we begin on this? Well, there's really only one place that we have all the information to do anything at all, and that is with the osmotic pressure. We know that pi is equal to nRT over V. Well, we know the osmotic pressure, the temperature, the volume, and so we can actually solve for N. N is going to equal pi V over RT. So let's look at what we have. We've got osmotic pressure of 3.97 atmospheres. 3.97 atmospheres. And the volume is 37 milliliters. Let's convert that to 0.037 liters over R. That's 0.08206 liters atmospheres per mole Kelvin. And the temperature was what, 297? 297 Kelvin. Okay, let's go ahead and pull up a calculator and see what we get. 3.97 times 0.037 divided by 0.08206 divided by 297. That gives me about 6 millimoles. And so I'm just going to write it actually up here in this corner. That N is equal to 0.00603. 6027. We'll carry an extra sig fig there. Okay, so now we know the total number of moles. Now that's the total number of moles of sucralose and what's the other one? Whatever the other compound is. Vitamin C combined. And so how does that help us? Well, we're going to have to build up a system of equations that are going to sort of help us out here. We do know one other thing. We know that the total mass is equal to 1.317 grams. Okay, and we have the chemical formulas for vitamin C and for sucralose. So we could look those up, and those are known to us as well. So how can we even begin to start with this? Well, I know that the mass total is going to equal the mass of vitamin C plus the mass of the sucralose. I don't know what those masses are, but they add up to the total mass. That makes sense, right? And I know that the N total is going to equal N of vitamin C plus N of sucralose. That's pretty easy as well, right? That makes perfect sense. Well, we can also recognize that the number of moles for anything is going to equal the mass times the formula weight or the molecular weight or the molar mass. So N equals M over M. We can go ahead and plug that in here. NC is going to equal MC over the molecular weight of vitamin C. And the number of moles of sucralose is going to equal the mass of the sucralose divided by the molecular weight of the sucralose. Sorry, let me make sure you can see everything. I think we're done with needing those for a moment. Okay, and why does this help us? Well, we can let's solve for the mass of the sucralose in terms of the mass of vitamin C and the total mass. So we know that MS is equal to M total minus MC. And now we can take this and plug it in right there. And I'll go ahead and do that. So this will be M total minus MC. And now this looks like a mess, but let's investigate it. N total is a constant we know right there. The molar mass of vitamin C, well, we can look that up. We'll look it up in just a second. The molar mass of sucralose, we'll look that up in just a second as well. The total mass we have right there. And so there's really only one unknown here. And there it is. So this is actually now solvable. We were able to combine the mass balance and the mole balance equations in order to get an equation that is solvable. It'll be a bit tedious algebraically, but it is solvable. So let's start putting in numbers that we know. What is N total? That's going to be 0.006027 moles. And what is the total mass? That's 1.317 grams. What is the molecular weight of vitamin C and the molecular weight of sucralose? I'll look those up. Pause it so you... Okay, so we have the mass of vitamin C of 176.12 grams per mole. The mass of sucralose at 397.64 grams per mole. Now, there are two ways to solve this, and one is to just go through the algebra yourself. It'll be a bit tedious. The first thing we'll want to do is separate these two terms. And so we'll have 0.06027 moles is equal to 1 over 176.12 grams per mole times the mass of vitamin C plus 1.317 grams divided by 397.64 grams per mole minus 1 over 397.64 grams per mole times that mass of vitamin C. We separate those two out, and now the way forward I think becomes a lot more clear. We can combine these two terms and we can subtract this over to that side. So let's do that real quick, and I'll go ahead and erase everything that we have up here. And we'll continue this problem at the top. Okay, so we'll pull up the calculator, and what I'm going to do is take 0.062, oops, no, 0.06027, and I will subtract that quantity of 1.317 divided by 397.64. And that gives me 0.05696. 0.0, what was it? 5696. That will be moles. And then on the right side, we'll combine the 1 over 176.12. So 1 divided by 176.12. Oops, 176.12 minus 1 divided by 397.64. And that's going to be 0.003163, 0.003163. The units here are actually moles per gram, and that's multiplied by the mass of vitamin C. And now it's just a matter of dividing by 3163, okay, on both sides. And so the mass of vitamin C is going to equal 0.05695, which is our 12th output, divided by 0.00316. And that can't be right. I've made a mistake. Okay, well, you gotta watch me squirm here a little bit. What have I done wrong? .06027 minus 1.317 divided by 397.64. That looks good. And 1 over 176.12 minus 1 over 397.64. Well, I don't see where I've made a mistake. So to be honest, part of my point of doing it this way was to show that it can be done, but it's a bit tedious, and part of the problem of that tedium is not just that it's no fun, but that there are opportunities to make mistakes. Ha! I found the mistake. All right. There should have been one more zero here. 0.0060207. So if you can see on my calculator down here, that's much better. Okay, I've made that correction. And so now it's this 0.0596. That's not right. It should be 0.002714. 0.002714 moles. Okay, and so now we're going to take 0.002714. We'll divide that by the 0.00316. That's more like it. And so our mass of vitamin C is 0.858. And 0.858 3196 divided by the total mass of 1.317 times 100. That makes it 65.2% vitamin C. And I guess that would make it 34.8% sucralose. And that's just because I know it needs to add up to 100%. Let's check if I got it right. Because we do have the answer displayed there. 65.0 and 35.0. So little bit of maybe I carried too many or too few sig figs on intermediate calculations, but that's basically the right answer. Now, I want to point out that for problems like this, I'm okay with you using an outside tool, maybe like something like Wolfram Alpha. Okay, let me make sure that's visible to you. Here we are. This is wolframalpha.com. And wolframalpha.com is just a easy sort of an online graphical calculator. You could do this with your graphing calculator as well, but frankly these days it's easiest to use a tool like Wolfram. So I'll just write that. I'll just write this original equation right here before we did any of that silliness with algebra, as if we lived before the age of computers, and I'll just input that formula. I'll say, I can just call it M, that's all right, Wolfram's smart enough to figure out what I mean. M divided by 176.12 plus 1.317 minus M divided by 397.64. Okay, so hopefully you can see that I've just sort of input that equation. I had to be a little bit careful with parentheses right here, but I hit enter, and you'll notice it says here it assumes that M is a variable. So well done, good job Wolfram Alpha. I did intend for M to be a variable, and it will give you all sorts of information. It'll try to simplify it. It'll try to graph both sides of your equation, but what we really want is down here at the bottom, the solution. It says M is equal to 0.858, which is what we calculated. So use Wolfram Alpha for very complex problems, if nothing else, to check your algebra and make sure that you've gotten it done correctly. Okay, so the next problem, I think this is problem 36, is also a very challenging problem. So let's take a look at that. We have 22.9 grams of an organic compound. We don't know the formula of the compound, but we do know its composition by mass. Mine is 65.45% carbon, 5.5% hydrogen, 29.06% oxygen. You dissolve it in 885 grams of benzene, and the freezing point is 4.29 degrees Celsius. The normal freezing point of benzene is 5.49 degrees Celsius. So what is the molecular formula for the organic compound? Assume the compound is molecular and so it does not ionize. In other words, that it has a Van 't Hoff factor of 1. And we're given Kf values for various solvents in the colligative constants table. So how are we going to solve this? We're given a percent composition, and we're given a freezing point depression, and all of this we're supposed to use to find the molecular formula. Well, again, let's start with the colligative property. That one seems like something we can get a handle on. We know that delta TF is going to equal negative KF times the molality. So let's start putting in some numbers here. We know that the normal freezing point is 5.49 and the new freezing point is 4.29, and so that is a delta TF of negative 1.2 degrees Celsius. Is that right? 5.49 minus 1.2 would be 4.29. So that's our delta F. That will be negative. What is the freezing point constant for benzene? Looks like 5.12 degrees Celsius per molal. 5.12 degrees Celsius per molal. And the molality is going to be N, the number of moles, divided by the mass in kilograms. We used 885 grams of benzene, so that is 0.885 kilograms. Okay, so I've done it this way. Finding the molality as an intermediate step is certainly a possibility, but I thought we'd just jump straight to N, the number of moles. Let's pull up the calculator. N is going to equal a negative 1.2 divided by a negative 5.12 times 0.885. And we get N is equal to 0.207. 0.2074 moles. And now we can do something very clever, because we know the total amount that we dissolved. It's 22.9 grams. And we know how many moles that was, so we can now find the molecular weight, or the molar mass, of our compound. It's just the grams. Sorry, I want to double check here. 22.9 grams divided by the number of moles. 0.2074 moles. That's going to give us grams per mole. So 22.9 divided by our previous answer there. And it looks like our molecular weight is 110.4. I'm going to go ahead and write that up here in the corner. And we don't need the colligative properties anymore. Our molecular weight is equal to 110.4 grams per mole. All right. Well, that's nice. How can we proceed from here? Well, we're given a percent composition, and even though we have a 22.9 gram sample, we're going to ignore that. We're actually done with that information. All we need to do is take these percents now and convert them into an empirical formula. And this is actually a 1210 material. This is a good review of, I think it's chapter 5 in your textbook. An analytical technique called combustion analysis would give you these values. And actually the easiest way to deal with this is to assume you have a 100 gram sample. And so that can turn all of your percentages into into grams, right? Like 65.45% carbon is going to be 65.45 grams of carbon. So 65.45 grams of carbon. And then I know it's 12.011 grams for every 1 mole of carbon. So let's figure out how many moles of carbon would be in my like hypothetical 100 gram sample. 65.45 divided by 12.011, and I get 5.449 moles. 5.449 moles of carbon. Well, we'll do the same thing with our quantities of hydrogen and oxygen. So we have 5.5 grams of hydrogen and 29.06 grams of oxygen. Okay, at this point we don't need to see sapling anymore. Okay, hydrogen is 1.00794 grams per 1 mole, and oxygen is 15.9994 grams per mole. Let's figure out how many moles of hydrogen and oxygen we have. 5.5 divided by 1.00794, that's 5.457 moles of hydrogen, and then 29.06 divided by 15.9994, and 1.816 moles of oxygen. So we could write like a formula of C 5.49, H 5.46, O 1.82, but you've never seen a formula like that before. What we really want to do is reduce these ratios mathematically. So we'll divide them all by the smallest number, which is 1.816. Divide by 1.816, divide by 1.816. So this is going to give us 1 oxygen. Let's figure out the carbon and the hydrogen. 5.449 divided by 1.816. That's 3.00 carbons. And 5.456 divided by 1.816, and that's 3.00 hydrogens. Ooh, we're almost there. Right? This means we now have good ratios. We can give an empirical formula of C3H3O. And finally, let's figure out what is the mass of that empirical formula. Well, I'll just do this one in my head. 3 times 12 is 36, and 3 from the hydrogen, and 16 from the oxygen. So that's 36 plus 3 is 39, 49, 55. 55 grams per mole. So the mass of the empirical formula is 55 grams per mole. The actual molar mass of our unknown compound is 110 grams per mole. Well, what do you know? This number is double that number, which means that the molecular formula is double the empirical formula. In the end, we should have C6H6O2. And let's just go back real quick and check that answer, C6H6O2, and that looks like that's correct. Okay, so good luck with your own numbers.